Hello, my name is Betsy Scott Hall, and in this video I'm going to tell you all about phthalates and just how controversial they really are. Now you might be wondering why I have a cover of Fleetwood Mac's Everywhere to begin with, and this will, I hope, become more apparent as to why later in the video. So getting on with it, this is the object of controversy, this is a phthalate, and if you have problems with pronouncing things like I do, then there's how to say it below. Perhaps you've heard of them because it turns out they're actually super popular in the news. For instance, this, and there's another one, and this, and this, and this, and this. But what actually is a phthalate? What do they do, and what's the big deal about them? I'm afraid to answer these questions, we're first going to have to go into quite a bit of context. I'll introduce this to you by telling you that phthalates are mainly used as plasticizers on a polymer called PVC. We'll start with what a polymer is. A polymer is essentially a macromolecule made up of smaller units called monomers. So here is the polymer we're focusing on today. This is PVC, polyvinyl chloride. Funnily enough, it's used to make vinyls. Down there's just a reinforcement of what a monomer is, and the monomer of PVC is chloroethene, just down here. Now, when you Google PVC, the first image that you'll see is this one. These pretty rigid looking tubes, but PVC actually has loads of other applications. PVC is used in flooring, hose pipes, insulation around wires for toys, in childcare, in medicine, for instance in blood bags and packaging, and also in plastisols as well. Now you may have noticed that in all those applications the PVC was not rigid but soft and flexible, and this is all down to plasticizers. Now plasticizers are molecules added to polymer matrices to make them softer and more pliable. They even lower the glass transition temperature, the temperature that's above which a material becomes flexible. Let's also note that there are two different types of plasticizer. The first is internal. Now, these are monomers that disturb the ability of the polymer strands to pack closely together. This means that the individual strands have more room to move around, allowing the material to become more flexible. The second type is external, meaning instead of monomers that become part of the structure, they are molecules that form secondary bonds between the polymer strands. Using secondary bonds like van der Waals or hydrogen bonding, for example, they stick between the strands and drive them apart. This achieves the same effect in allowing individual strands more room and the polymer to become more flexible. In this video, we will be focusing specifically on external plasticizers, which is what our phthalates are. Next, I want to talk about plasticizer efficiency. And this might seem off topic now, but when we look at the problems with phthalates later on, its relevance will become apparent. Plasticizer efficiency depends on how great the rate of diffusion of plasticizers are through the polymer matrix. Now, the larger and greater in molecular weight the plasticizer is, the slower the rate of diffusion. Hence, the plasticizer will have a lower efficiency. Now, size and molecular weight are dependent on the same thing, the number of carbons on the ester side chain. So here, just for summary and reference, is a picture of plasticizers in a polymer matrix. And as you can see from the tangled strands on the top image, it would be harder for larger plasticizers to get through these tangled strands and separate all the strands individually. And so the last thing I want to say about plasticizers is that they're usually esters, and actually a whole range of different esters are used, including, most relevant to this video, phthalates. So context over, back to phthalates. Phthalates contain both ester functional groups and a benzene ring too. And the starting product for phthalates is phthalic anhydride, shown here. Phthalic anhydride is usually reacted with an alcohol in the presence of an acid catalyst. For instance, you can make this phthalate, bis-2-ethyl hexyl phthalate, using the alcohol 2-ethylhexanol. And it is by using different alcohols that we can give phthalates different degrees of permanence and performance. Just by using different alcohols, all these different phthalates are synthesized. Now, it's not just that all these compounds are phthalates that ties them together. They are also all banned in the UK and EU. This is the UK government article it published on the 17th of June 2019. And just to show you the relevant bits, sorry it's a bit of a wordy slide, it basically says that it will be illegal to sell plastic products containing those 4 phthalates. And just to prove to you that I'm not lying and it's definitely the phthalates that I just showed you, here are them referenced at the bottom of the article. Now, the reason for this isn't really mentioned in the article, but it's because these compounds were found to be endocrine disrupting chemicals, EDCs for short. They are what they say on the packet, chemicals that disrupt the endocrine system. The endocrine system is basically in charge of the hormones in your body. Hormones essentially being chemical messengers. Hormones are necessary for controlling your growth and development, metabolism, reproduction, your immune system, and even your behaviour as well. Now, EDCs can work in two different ways. They can either block active sites of hormones, or they can mimic them, both of which have adverse effects on your body. Having similar chemical structures, these phthalates also have similar properties as endocrine disruptors, and their most discussed effect is that on testosterone levels. This molecule here being testosterone. To give some examples, in one study on workers exposed to DBP, they found that not only were their testosterone levels decreased, but their sperm count and motility as well. DIBP, meanwhile, having similar effects with testosterone levels. But our headline act is really DHP. You might have seen it referenced all the way through this video. This is the phthalate that's usually mentioned first in any paper or article, and for some reason is generally more talked about than the others. In a 2008 report from the EU, these concerns are listed in its risk assessment of DHP, and I'll put the risk assessments for our other phthalates in the further reading section. It's just they're all quite similar, so if I showed you all of them, I'd be repeating myself an awful lot. Anyway, here they are. Again, fertility and testicular issues, which are probably due to that decrease in testosterone. Now, this is probably a good time to talk about where this data comes from. And I just want to warn you, if you're sensitive about violence against animals, now might be a good point to skip over this section. But yes, testing like this usually begins with animals, and if you want to read this 588-page EU report, you'll find testing was done on fish, chickens, rats, even people, and this has been happening for quite a while too, some sources dating back to the 70s and 80s. Anyway, tangent over. So here are two examples of DHP testing on animals. The first one is on female leghorn chickens, and having been exposed to the DEHP, the chickens stopped producing eggs and had normal ovaries. These chickens also had hypertrophy of the kidneys and liver, hence the worry about toxicity to kidneys in humans on the EU report. And then there's the concentration of DHP they used as well. Then a test on male rats, both when they were feti and pups, showed that food with concentrations of 100 ppm of DHP caused irreversible testicular damage. Now, of course, these results don't transfer directly to humans, but it still gives caution to perhaps similar effects. This EU report also went into the routes of exposure, which I'm just going to extend on. The first being dermal, which is essentially just skin contact. The second is oral, which pertains to anything eaten or chewed. This is why it's such a worry when it comes to phthalate exposure with infants, especially because young/developing organisms are supposed to be the most vulnerable to them. And finally we have intravenous, which means anything going through the bloodstream. This means anyone using blood bags or on drips are exposed that way. So now maybe you understand why I opened by saying that phthalates were everywhere. They were in our products and they were also leaching into our environment. But why does this happen? Well, it's all down to the plasticizer's efficiency, which we learnt earlier depends on their ability to diffuse, in turn depending on their molecular weight. The problem is in using low molecular weight phthalates like DBP and DIBP is that they're too efficient and will happily diffuse out of the material. I guess this is kind of a light bulb moment for any of you wondering why phthalates were used for so long if they're so dangerous. It's just because they're so efficient at what they do. And just whilst we're talking about DBP and exposure, here's a statistic from 2002, and if you read it you can definitely understand why there was such a worry about phthalates affecting infants. So what does the future hold for phthalates? Well, it seems they're slowly being phased out. Luckily there are 30,000 potential plasticizers to choose from, and we'll explore two routes: synthetic alternatives and bioplasticizers. But before we go on to that, this is the challenge for chemists to solve with external plasticizers, to achieve the balance between efficiency and leachability. Effectively, the problem is that plasticizer molecules need to be small enough in molecular weight to diffuse well, but high enough in weight so that they don't diffuse out of the material so easily. One way to go about this is through synthetic alternatives, essentially to design plasticizers to be slightly heavier with around 8 to 10 carbons in side chain length or backbone length, but also to mimic phthalates in terms of their chemical properties by containing similar functional groups. An example of this chemical mimicry can be seen in benzoates, which, like phthalates, have an ester group and a benzene ring. So the alternative to the alternatives are bioplasticizers. These aren't particularly new, they're just not very talked about. Obviously, with their name and from the previous slides you can guess they're not petro-based, but the aims are still pretty similar, aiming for low toxicity and decent efficiency. But another aim is to reduce cost, and this cost is really from the amount of processing it takes to make them. Polysaccharide plasticizers are a great example of that problem, but other feedstocks include oils derived from soybean, castor and linseed. And another way of doing it is using, or rather reusing, waste. So if you're interested in this sort of stuff like I am, go ahead and look at the source below. It's a really good one, to be honest. And then here is a graph of synthetic petro-based versus bioplasticizers, synthetic in the orange and bio in the green. It's looking at how their global production in tonnes will grow, and the fainter blocks are that way essentially because they're only forecasted. But as you can see, even though production as a whole will increase, the synthetic petroleum-based route is still preferred. So moving away from the future and into the present, this is the end of the video. I hope you enjoyed watching it, and I hope you might have learned something. And if you're interested in learning any more, then here's a bit of further reading. Also, just to note, any pictures that are not credited were drawn by me on ChemDraw. Anyway, thank you for watching.